All right. And with that, we better get going. I see you have 34 seconds. No, that's enough for a basic introduction.
Mm-hmm.
Eric, how long have you been here now, Eric?
4 years.
4 years.
Yeah, since 2015. Yeah.
So 4 years.
Well, I started in the masters and then
Masters.
converted into the PhD.
Now
So
it's officially 4 years.
give me a little bit extra time because of
You
that.
should be. You should do your candidacies now.
Yes. Yes, maybe. Who knows? Who's to say?
Okay. Eric,
Yeah, pretty soon.
done a variety of interesting things, and this is going to be one of them, I think.
Yeah. This is an interesting topic that came out of some work I was doing with Martha. Got me interested in off-policy learning and better ways of doing important sampling. Yeah.
So, welcome, Eric. Like I said.
Thank you. All right, so yeah, as you can see, we talk about visit distribution corrections today. I've heard that off-policy learning, especially in this research group, we really seem to talk about off-policy learning as being high variance inherently, and we just sort of take that for granted. And that's sort of something that people just sort of, assume is true and don't look any further. So today I'm going to show you that it's actually, the variance issues are possibly or largely a problem or an issue of the chosen solution method and not of the true problem, underlying problem. And I'm going to do that by presenting an alternative approach that has recently popped up in the literature. So this is sort of a summary of works that have come out in the last few years. None of this is actually my work, so don't blame me. So right, we have off-policy learning, and it's important to motivate the problem and why we want to actually do it. So off-policy learning is learning about a policy without following it exactly. So I like this example or this definition because it really it has a couple things in it that are helpful, which is, so one of them is that you do have to occasionally take actions that the behavior policies would take. So you do have to follow it to some degree, but not exactly. So an example of maybe this sort of off-policy learning is learning about the minimum time it takes to get from like your home to the university by exploring a bunch of different routes. And learning the best way from that exploratory data. So, right, why is this interesting, right? Why do you have to sit through a talk and listen to me go on about this? It's interesting because off-policy learning is extremely important to reinforcement learning in general. It gives a reinforcement learning agent the ability to learn from suboptimal data. And that suboptimal data can be exploratory data. It can be data that's generated by humans. It can also be just random data. Another thing that off-policy learning gives us is a potential increase to sample efficiency. Or I guess I shouldn't say sample efficiency. I should say it uses data more efficiently. So you can reuse old data, like an experience replay, by, or I guess old data that was generated by a different version of the policy. You can also learn about many policies in parallel, like in the Horde architecture, another way that we can learn more efficiently, I guess. And then the third thing that's very important for any sort of application of RL is safety. And we would like to be able to, learn without direct control of the environment, because giving a newly initialized learning agent control of a self-driving car or a nuclear power plant is a terrible idea, right? it's like the fast way to an AI winter and a nuclear winter. So, you had a question?
Regarding optimal data, what's optimal data?
Oh, I guess, yeah. So what I mean by this is it has the ability to learn an optimal policy while experiencing suboptimal data. So data that is generated by a non-optimal policy. And like I mentioned before, that could be like a random policy. So given a problem and just running a randomly choosing actions, you can still learn the optimal policy for that environment with off-policy learning. Yeah, so it's a really important thing to research, but I know what you're saying. Hey, Eric, doesn't it have crazy variance problems or something? I've heard this is really bad, and we would like to do it, but there's some roadblocks in the way. So I maintain that the importance sampling on policies has variance issues, which is a conventional approach that is built into a lot of our methods. Whereas this new approach, importance sampling and visit distributions, doesn't. It doesn't have the same variance issues. So that's really exciting. If this is true, we can get the benefits of off-policy learning without paying this cost of instability due to high variance. Yeah, so just a minute. Right, so this is a bit of a really short overview because you've all seen these talks before, you know exactly how it's going to go, but just wanted to give some motivation at the beginning and then a little bit of background so that we can talk about this precisely. And then I'll overview the conventional approach and the alternative approach, and I'll give a few examples, hopefully to intuitively motivate this. Right, so this slide I'm pretty sure is mandatory on all of our T time talks. It is the agent environment interface, and yeah, at each time step T, the agent interacts with the environment, receives the current state of the environment. I'm assuming this is like fully observable. I don't want partial observability right now. And uses a policy to select an action and receive some reward and view the next state. So I guess I should spend a little more time on this. Right, so no, I shouldn't. All right. Okay, cool. So here's some more background. From this interaction, we get trajectories, which are sequences of states, actions, and rewards. And then in that trajectory, we have these rewards at each time step. We want to sum them up, possibly discount them, although Abhishek says no. And we want to predict this return here, which is, yeah, right there. So then the value of a state is the expected return, starting in that state and following the policy pi thereafter. And because of this discounting parameter, we can go on forever and we'll still have a finite sum. So now that we've gone over that, there's a prediction goal and the control goal. Prediction essentially means you want to learn the value function for some target policy pi while following a fixed behavior policy b. In control, we want to learn pi itself while following b. But I'm not going to talk about control because it's really hard. So today I just want to focus on prediction because it is much simpler and cleaner for the purposes of explaining these topics. Right. So we have this issue where we're following B, we're sampling according to B, sampling states according to B, and we want to, however, compute the value, the expected return, as though we were following pi. So there's this discrepancy between policies where they're each assigned some probability density or mass, I guess, if you're in the discrete case, to each of the actions in a state. And they're going to assign this mass differently. So we have some discrepancy that we need to make up for to get an unbiased estimate of the expected return, or the expected, return. So here's a really simple, actually, just 1 minute. Are there any questions up until now? It's all good?
So are you going to find this behavior policy so that you will the best behavior policy to reduce the variance? Is this the objective of this talk?
The question is the objective of the talk to find the best behavior policy for reducing this variance? No, I'm going to treat the behavior policy as fixed so that it can't change. I don't have access to it. I just get some samples of it, and I want to learn the target policy pi, and I'm not actually going to directly attack this variance issue. I'm just going to show that there's another approach that doesn't have this exploding variance problem, and that's the way that I'm going to show that there's a lower variance way of doing it. Sort of indirect, I guess. Any other questions before I move on? Cool. So this is all background. Everyone knows that. So I've got importance sampling up here as the main way that we reduce this discrepancy between policies. So I've just put this down to a really simple bandit case so that we can talk about it and sort of get an intuition for how it works. Right, so there's only one state. We don't have to worry about that. We want to know the expected reward would be under pi. We only have samples for b. So we're going to correct this discrepancy by scaling our samples according to this likelihood ratio so that we can change an expectation under pi on this one-step reward to an expectation under b for this one-step reward. So yeah, often this ratio, this likelihood ratio is called rho, an importance sampling ratio. Are there any questions on this? Good, that means I got the notation right. Right, so straightforward extension to correct returns instead of, which are products of random variables instead of one-step random variables, like in the bandit case. So here we have this, right, I guess we'll come over here. So we have this expected value of the return given that we start in state S, and essentially we are using the previous importance sampling formula to correct the first reward, which is a random quantity. Anyways, then for the next step, we have to correct this whole trajectory. So we're correcting by both the first and the second importance sampling ratios, and then on to the third and fourth, and so on and so forth. So this is a really gross, ugly way of writing it, but it's essentially we have this product here that scales with, it grows as with the length of the trajectory, t, big T. So using importance sampling this way, yeah, can suffer from exponentially high variance as the product of importance sampling ratios grows with the trajectory length. So doing this, right, so you can see why this adds variance that isn't necessary, maybe, from this example. So say that you're coming along a trajectory of experience and you're in a certain state and you have two different actions you can take, and they both take you to the state S2, the same state. So in this example, the probability of visiting S2 is the same under both policies. It doesn't matter that the different policies give you a different probability or different mass probability on each action, because the actions are irrelevant. They don't actually matter. The state you visit is going to be determined by the environment. It's sort of an example where, like, I guess we kind of forget that it is kind of a two-player game between the agent and the environment. So the agent takes an action, the environment responds. It doesn't really, like, the environment may not care that the agent took a different action, right? It can deterministically control where you go, put you in the same exact state, and then your difference in policies is irrelevant and doesn't matter. So I guess pardon?
In general, it does.
In general, it does matter, but there are some situations where it doesn't, and this is a really, really simple one. So if you were to loop several times, you would experience this over and over, and even though you're visiting the same state, our conventional methods just treat each state that we visit as being different, which is good if you don't have loops, I guess. Then that's the best you can do. But yeah, so you can see, I guess, hopefully intuitively, a little bit why this adds more variance than would be necessary. Yeah. So, right, a different approach can be to do corrections and importance sampling on the visit distributions. In this case, I'm going to talk about so in this case, I'm going to talk about state action visit distributions. It's a little simpler to talk about them than state visits, because when you arrive in a state, then you have to consult your policy, and then you have to do corrections on both the visit distribution and the policies. So if I do it on state action visit distributions, you don't have to worry about the policies themselves and that important sampling ratio. Right, so the average, I guess this is the average reward, or I guess the value of a policy, yeah. Okay, this is assuming it's from the start state to clarify the notation, so that it's very, very simple, because the ideas are kind of a little tricky, and I didn't want them to get mixed in with the notation and lost with the notation. Right, so here we have states in action sampled from the stationary visit distribution. And then we basically can just sum up the rewards that we visit this way, that we receive this way. Could be, well, we're not summing them. I guess we're doing a weighted average of them. Okay, so right, instead we could do this important sampling on the state action visit distributions themselves that are induced by the policies. And if we do this, then we just get this, to correct a whole trajectory, we just get, wait, no, that's not this. Yeah, never mind. If instead we want to correct an individual step, we can do it with just this ratio that is not a product, it does not grow over time, which is very, very helpful in situations like this. So this is the intuitive example that really sort of drives home the difference in the two approaches. So in this example, we have a ring and we have one policy. So this should be B. I forgot to change that. Right, so if the behavior policy says with some probability it's going to go left, or I guess clockwise, and some probability it's going to go counterclockwise, the target policy says the opposite. So if we set, I guess this is also row, which is bad. I should have changed that as well. Anyways, if you set that to something high, like 0.9, then it's going to be extremely high variance under the conventional method, because you're going to have this product of important sampling ratios that's going to grow and grow and grow forever, essentially. But yeah, the two policies are actually symmetric, which means they have identical stationary state distributions, which means that you only need to correct based on those densities, and you'll get an unbiased estimate from your behavior policy. So this is really cool, because this sort of shows that you can do this in a way, certainly for this example, in a way that is much lower variance than our conventional method. And it's really, yeah, it's really, really exciting, because it's sort of been taken for granted that we couldn't do things like this. We sort of use this, Rich?
You told us how we can do it.
Right, so that's the thing that I didn't want to get into in this talk, because essentially this is like a density ratio estimation problem, which is, there are many methods for solving this. There are some like you can do a TD method, you can do some with convex optimization and whatnot. So there's many papers that have come out doing things like this, and I didn't really want to get into a extensive literature survey showing all the different ways you can do this. But yeah.
I would have thought it's impossible.
Really?
Yeah.
Why is that?
Because you don't have, well, you know, if you can have, if you could represent the state space explicitly and do counts, maybe you can do it. I don't know. How are you going to do it?
Counts. Huh. Do you mean like, so if you normalize counts, you have a distribution, right?
I've never seen any way to do it.
Okay. Maybe I should do another tea time talk where I talk about the second half of this. Yeah. Interesting. All right, maybe I can meet with you and talk afterwards about the different ways that people have come up with to do it. E?
So I guess if the space of the state in action small, then you could have, like, potentially you can have some way to do it. But if you consider infinite state action space, then this ratio can potentially be something that you're compounding. And I think the only possible way is to build a generative model that can generate this state and action according to your target policy.
That's interesting.
But even if the important sampling ratio, like if you only correct the action, that's because we only care about few actions, choices. If you consider infinite action choices, just like your ACE paper, you can't do that role to correct your.
The issue in that paper is we can do it for continuous spaces. We just can't do we can't do this important sampling correction on deterministic continuous policies, because then your policy is just like a Dirac delta, and you just have an undefined ratio there, I guess. So we could still do it for continuous spaces if we parameterize the policy properly, but you might get some variance issues in the sense that, like, because of support, or I guess not support, because the densities are wildly different, you may have a very small density on one section, a very large on the other. But that's not as bad as, like, the product of importance sampling ratios, I would say, because that's variance in addition to this ratio that may be a large constant. Yeah. Any other questions, Abhishek?
So, is this what the COP-TD or Bellamaire's paper kind of tried to do?
Right. So the consistent off-policy TD paper is one way of doing this online and incrementally, which is pretty cool. They use function approximation to represent this ratio, and so sort of was what I was sort of going to say to Yi's response, is that you can use function approximation for these ratios the same way that you can for an action value function, because that's really like we just have a function of state action pairs. So have two functions, divide them. You can also do the ratio directly instead of doing each individual density and dividing. So yeah, there's this COP-TD paper, and then Mark Bellamaire's extension to that with the discounting parameter. They call it discounting, but it's like interpolation. There's a couple of other methods that have come out as well. There's a paper called Breaking the Cursive Horizon, and it deals with using the Bellman equations to derive an optimization target. There's another paper that came out super recently that's on arXiv that does a similar thing, but has they form a different optimization problem, and they use duality to come up with a way to optimize it that's independent of the behavior distribution. Sorry, independent of the target distribution, so that they just have this data that's been collected from various different policies, and they can optimize. They can, for a given policy, they can solve this convex optimization problem and come up with this ratio directly, and it seems to be really, really good in practice. Rich.
This won't give you the value function. This equation doesn't give you the value function.
Right. So I sort of danced around that by saying that it's the value of the policy that we're computing here, which is like average reward, which is not the value function, right? So there are ways of doing that as well. I just wanted to avoid the really convoluted notation required for that. It's not that much more convoluted, but this is really simple and something that I would rather present.
Why does
Is it here?
have lower variance?
Lower variance?
Apart from that, one example.
Right.
An MDP where this method is high variance, then obviously the equation.
Why does it have lower variance?
Is it a general idea, or is it?
It's a general idea that applies to most situations where you have, like, so I mentioned this a little bit earlier, where you have loops, and if you don't have loops, then this isn't much of a gain, because in the worst case you will have to do this product of importance sampling ratios, right, to get, or rather if you do that, that's not going to, it's not going to add any extra variance. Sorry, I'm confused. I'm thinking of the first example that I gave with the split. So I guess the property of this example that makes it really bad for this conventional method is that it loops and it's continuous. But it loops and continuing, I mean, so that you just have this product pile up over time. And because you're looping, you're going back to the same states over and over. But our estimator doesn't take into account the fact that we're doing that. Like our conventional estimator just keeps multiplying these products of importance sampling ratios as though it's visiting different states. When really, it's visiting the same state, so it doesn't need to do the corrections. So, yeah, does that answer your question?
You don't need to take products, even when you're estimating the value.
So there are you could do that as an estimator, and that's one way of doing that. But it's not the only estimator we can use, and it's not a very good one for that purpose. Roshan?
I just had a comment which kind of addresses this. So the intuition is exactly the same as using returns versus using backups, right? So if you have a sequence of states that never repeats, then in principle you can't do much better in the return, right? But by using the Markov property and using the value of one state to bootstrap another state, you're kind of taking advantage of the fact that you're visiting the same states again and again. And the same thing happens here because the importance sampling ratio actually obeys a recurrence relation. You can write the importance sampling for one state as something times the importance sampling ratio for another state. Right? So that means that if you visit the same state again and again, you don't need to just keep multiplying the importance ratios forever. Once you come back to a state, you can use the Markov property and do it that time. So they're just kind of so now the variance of this scales with something like the size of your state space rather than the length of your trajectory.
Right. That's a really good point. That this sort of approach with visit distributions is leveraging the Markov property instead of doing sort of a Monte Carlo style rollout.
But if you're willing to use the Markov property, then you
Right.
can just bootstrap. You also don't have to have products of importance sampling ratios.
Yeah, I'm suggesting. You mean bootstrapping? Yeah, right. So that's a different estimator that you can use. And I think that's the one that's used in the COP-TD paper. So they have this bootstrapped objective that they use to create that. Rupam?
There are two kinds of discrepancies. One is the discrepancy in the conditional distribution of the return. The other is the distribution of the state visitation. Which one you're correct?
So the question is that there's two discrepancies. There's a discrepancy in the state visits, and what was the other one? In the return?
Yeah,
Conditional distribution of the return.
which one you're correct?
So the state distributions.
So you're not saying that you are reducing the variance in the estimation of the expected return.
No, that's right.
You're not. That we still have that problem.
Right.
Okay. So now the question is for. So we can call them like post correction, pre correction. Yeah. So we are doing the pre correction.
Yeah, this is essentially intending to do that.
So what is the alternative? You're saying that this has low variance.
Right.
What else we could do? Although,
What else could we do?
yeah, which one has more variance?
Oh, okay.
That approach that we give us more variance.
Right. So if we use the conventional estimators and use that to do pre-corrections, then we have this variance problem that exists with the conventional methods. If we if we instead use this alternative approach to estimating this, we don't have the same variance issues for prior corrections. I think essentially the posterior corrections will be the same because we're just correcting like the policy at sort of one, I guess afterwards, one step. I don't know. Sina.
So I just wanted to ask the same thing as Rupan. So there are two things that you can be corrected for when you get an
Right.
One is the state visitation distribution, and the one is the distribution of actions given space.
Yeah.
So what you're writing for here is the state visitation distribution. I think.
So this example does both, in that this d pi of SA is the visit distributions for state and action. So it's essentially the state distribution, like d pi of S times the policy, the probability of taking action A given that you're in state S. And then that's essentially what this term is. So it's doing both, right? Yeah, I think it's doing both. It's doing the state distribution plus it's doing the policies discrepancy as well.
I don't think this can be doing both. I think you
Okay.
So you should be able to do the exact same thing for learning the state value function, right? You actually switch from learning state value functions to state action values. So you should be able to do the same thing with state value functions.
Yep.
And then you're not going to be correcting for the distribution of actions within the space. The normal influence sampling ratio, you're not going to be doing the normal influence sampling ratio.
So if you do, I guess what I'm saying is if you ignore the actions here, like this is essentially correcting for the distribution between states, and then if you, yeah, I guess I shouldn't try to simplify this that much, then you're also correcting by this importance sampling ratio if you want to do it that way. The importance sampling ratio for policies, I mean. So that you've got your pre-corrections in the state visit distribution, and you're correcting based on that, and then you're also correcting based on the policy's difference in probabilities. So you're doing both prior and posterior corrections.
So you're running along, you're running into states according to behavior distributions, and you want to adjust for the fact that you would have a different probability of being in this state under the target policy. I don't see how you're going to know that. How you could possibly know that. So it's been a mystery for a long time. You know, we've always known how you might do this, and I feel like you're asking us to be impressed by you're not telling us how it's done. And I don't, you know, I'm still sitting here thinking this is a long-standing thing we've never been able to do.
Right.
And now you're telling me lots of people are doing it, but you're not telling me what they are.
Okay.
Yeah, I still think it's impossible.
Okay. Cool.
In any practical, real sense.
Interesting. All right. Well, I guess I'll make another presentation for talking about solution methods.
Okay.
Zahir?
In the solution methods, do they have some? Do they take a shortcut so that they don't have to estimate these densities, or they individually estimate these two densities?
So most of the time they do the direct ratio. They don't do they don't try to estimate two different densities and then divide by them, because numerically that's a terrible idea in general. So what they do is they essentially take advantage of the fact that these visit distributions can be expressed recursively, and then they sort of do this recursive. I guess they express this ratio as a recursion, and then they generate a lot of methods are generated from that expression.
So this problem, so if this method make it easier than doing density estimation in the usual way. So is this problem easier than doing density estimation?
Yes, because the densities are not arbitrary in this case. In this case, both the densities are have to do with like your visit distributions of a Markov chain induced by a policy. So you have some recursive structure there that you can take advantage of in a way that just arbitrary densities can be a lot more difficult. So that's where some of the papers that have come out recently are getting their, like that's how they're driving a better method than the existing density ratio estimation methods. Banafshe.
So, you're thinking that every time the value function that you want to approximate, right? Wouldn't it be another opposing problem here?
Right. So I was looking at this like a year ago, and I got stumped because I tried to do this with TD. So then trying to learn this ratio off policy is itself an off policy learning problem. So then I couldn't actually make any progress, and that's when I started looking up other papers and read about some of the other methods people had done. So if you try to do it directly, then yeah, that's that's true. But then if you take advantage of the fact that it's a ratio, you can derive some better methods. Some worse ones too, like there's a Bellman residual minimization based one. I don't know how. Anyways, does anyone else have questions?
Yes. Thank you very much.
1 second. Right. Okay.